Okay, we just discussed this problem in the class. Okay, and we found out what would be the current when we switch it to the position 1 after that amount of time. Okay. So, and we obtained 1.9 amperes. So now I want you to look at this problem. So what we have said that the switch was in the position 1 briefly. Well, for some period of time. It wasn't said. It wasn't said for how long. So what we are asked to find, how long does it take for the voltage across the inductor to drop to the half of its initial value. All right. So now we switch it to the position 2 like this, and now the load behaves. The inductor behaves as a source. Okay. If the inductor behaves as a source, we know what equations we need to use, that the potential difference in the inductor across the inductor as a function of time is given by its maximum or initial value, let me call it initial value, times what? Well, in the situation when time goes to infinity, of course it has to drop, right? So therefore we'll have this law which shows this decay in potential difference across the load as a function of time, so it goes to 0 at infinite times, and this is the mathematical equations we are going to use. All right, so but what do we need to find? We need to find how long does it take the voltage across the inductor to drop to half of its initial value. So we know that the initial value is delta V0, okay, at t equals 0, so that is delta V0, right? So you can see that if you substitute into this equation that t is 0, then the exponential of 0 will be 1, and this is the initial value. Yeah. So but we need to know when the voltage will be the half of the initial value. So that means that voltage is a half. Okay. And again, so the right hand side we just rewrite. And here we have exponential of minus t divided by tau. And this t we need to find, right? So we'll simplify this equation. We'll just cancel delta v 0 on both right and left hand side. So we have exponential of minus t divided by tau, and given by 1/2. Okay, so now we can take the natural log of both sides. So we'll get minus t divided by tau equals to logarithm natural log of 1/2. Okay, now we can solve for t. So t will be minus tau times logarithm of 1/2. Now I need to remember what tau is. Okay, what tau is for an RL circuit, and we discussed this in class. So somewhere over here we had the equation for the tau. I hope we had it. Okay, we had it in the very beginning over here. So it's L over R, right? So and we'll just substitute this L over R instead of tau into the equation we just derived. So it's L over R for tau. So we'll substitute it into this equation. So R is known, L is known. Make sure that you don't forget about millihenry. Okay, substitute in this equation and get the final result. I will let you do these calculations. So what I've got is 23.1 milliseconds. Please check if it's correct. Okay. So now there is another problem I want to consider, and that's the final one. So here I need to find the current through the battery. Okay, so the current through the battery. Let me right away indicate this current over here. After the circuit has reached its steady state. Okay, so it means that it was connected and it reached the steady state, and I need to find the current. Well, what do I do if the circuit has reached the steady state? It means that the current is constant. If the current is constant, it means that I can replace the inductance by just a piece of the wire. Okay, and forget about everything else about this inductance. The potential difference across this inductance is 0, so I can replace it with just straight piece of the wire. Well, if I can do that, that means that these 2 points are essentially just, short circuited, right? So it means that there will be no current through that resistor. If you don't believe me, you can compute that. Use the fact that the resistance over here through this part of the circuit is 0, right? Because it's just a straight wire, we assume that the resistance is 0. Consider that the resistance is 0 and compute what would be the current through that part and what would be the current from this to this part. So here you obtain that the current is 0. There will be nothing flowing through this resistor and everything, and here the current will be I. You can compute that, but it's also the rule that if it is short-circuited, then the current will be flowing only through this, through the wire, not through the resistor. But again, you can compute it. All right, so, and therefore I can simplify this circuit into the following one. Okay, this is my EMF, this is the resistance of 4 ohms, all right? So that's my simplified circuit, and now I can find the current through the battery, right? So the current will be given by the EMF. Well, the current is the same in the circuit, is the same as the current through the resistor, right? So and the current is given by EMF divided by the resistance, and by substituting the numbers, it's 12 volts divided by 4 ohms, and I will get the answer into amperes, so it will be 3 amps. Okay, 3 amps. So now consider the situation actually when we do the following. We'll just cut these things off after charging the inductor for quite some time. So we'll charge the inductor will be connected, but at some point, okay, we will like open that switch over here. Okay, so we will reach the steady state, and then we will open the switch over here, and then we will be able to simplify this into the following circuit. Okay, the inductance of this resistor, this inductor. Okay, so the energy we stored in the inductor will now be transported to the resistor, okay, and eventually so in this situation, the inductor would act as a source. Anyway, that's all that's all we didn't cover in the class. So and this is all I have in this video.